Welcome back. This is the second video on chemical equilibrium. Now remember, I'm just giving you an introduction to chemical equilibrium. This is for new chemistry students who are just trying to get a grasp on the foundation of chemical equilibrium, writing chemical equilibrium constant expressions, and so forth. Okay, so in our first video, we defined chemical equilibrium as equilibrium is established when opposing reactions have equal rates. Equilibrium expression is a ratio of the substances involved, and three things that I want you to remember when you write the expression. You must have a balanced equation. Concentrations are included, so we're looking at molarities, moles of solute per liter of solution, and we're excluding the pure solids and pure liquids. And then finally that the expression is dependent upon the stoichiometry of the reaction, not on the mechanism, and that the value of the expression, the value, is dependent on temperature. Okay, so let's have an example here. Okay, here's an example problem from our Haber process here, the synthesis of the ammonia. Okay, so here's a typical problem for an introduction to equilibrium. At equilibrium, a mixture of nitrogen, hydrogen, and ammonia gas at 500 degrees Celsius. Okay, notice that I gave you the temperature here because remember, equilibrium expression values are temperature specific. Okay, so at 500 degrees Celsius, this mixture consists of 0.602 moles per liter of nitrogen, 0.420 moles per liter hydrogen gas, and 0.113 moles per liter of ammonia gas. And our question is, what is the Kc? What is the equilibrium expression value here? What is that value? Okay, so the first thing we want to do is we want to write that expression. Okay, so Kc is equal to, now remember, it is a ratio of the concentrations and is products over reactants. Okay, products over reactants. Let's remember the three things. We must have a balanced reaction equation. Check, we've got that. Second, we are looking at concentration values. So we're looking at molarities, moles per liter. Okay, each one of the values we were given are moles per liter. Okay, given to us. Okay, and then the third thing that I wanted you to remember is that we exclude pure solids and pure liquids. Okay, each one of our substances, gas, gas, gas. Okay, so we're going to include all three of those substances. Okay, now we use square brackets to represent concentrations. Okay, that is most important to use square brackets. Okay, do not get lazy or foolish and use parentheses here. These are concentrations, and in chemistry, square brackets are representative of concentration values. Okay, so square brackets, and our product is the ammonia. Remember, products are on the right side, reactants are on the left. Our ammonia is 0.113, okay, square bracket. And then remember that our expression is dependent on the stoichiometry. So 2 from the balanced equation, so we're going to have an exponential power of 2 on the ammonia. Remember, this is products over reactants. Now let's do the reactants, square brackets again. The nitrogen value was 0.602 moles per liter. Stoichiometry on it is just a coefficient of 1. If it helps you to remember to put the 1 there, go ahead. And then square brackets for the hydrogen. Okay, and hydrogen's value was 0.420 moles per liter. Stoichiometry for it is a 3. So we're going to cube that value. Okay. And then we're going to solve this. We are going to solve this Kc, or equilibrium expression value. Okay, so we have 0.113. Okay, so 0.113, It's kind of hard to see the screen. Let me just put it over here. Squared. Okay, so 0.113 squared comes out to be 0.012769. Now, I am ignoring sig figs here on my intermediate calculations because, again, I'm going to round those at the final answer. Okay, and then our denominator here, let's go 0.420. Let's cube it. Okay, so 0.420 cubed. All right, and then we're multiplying that by 0.602. Okay, and our value for our denominator is 0.0446009, and it continues on and on. That's plenty. Okay, and then we solve that. And we get a value of 0.286. Now I'm carrying 3 sig figs because each one of these concentration values had 3 sig figs. Remember that leading zeros are losers. They're not significant. Okay, so 0.286. Now this value right here is considered our equilibrium expression, our value. Okay, 0.286 is what it is. Typically we don't put units on these, moles or liters or molarities. These are ratio values. Okay, now you may be wondering, well, what does that number mean? What does that tell us? Well, this value here is a ratio of products to reactants. So if this value is less than 1, so if Kc is less than 1, then what that tells us, gives us insight on, is that at equilibrium, the concentration, okay, the concentration of the reactants is greater than the concentration of the products. Okay, we're seeing that. If Kc were greater than 1, okay, if Kc was greater than 1, then what that would be helping us realize is that our concentration of our products is greater than the concentration of our reactants. So if Kc is less than 1, then what that helps us to see is that the reactants are most common, or most abundant, or present the most at equilibrium. If Kc is greater than 1, then our products are the most common species present once equilibrium is established, okay? Because this is just a ratio value of product concentrations to reactant concentrations, okay? Now, let's move on and let's try another example where we write the equilibrium expression, okay? So, here's another reaction for us. Okay. We've got a decomposition here of calcium carbonate, and we're going to calcium oxide and carbon dioxide. Okay, so let's remember, when we write an equilibrium expression, 3 things we must remember. First, we have a balanced chemical reaction equation. We have got it balanced, calcium 1, carbon 1 apiece, oxygen, there's 3 on the left and 3 on the right. So, number 1, balanced equation. Number 2, we are going to be referencing the molarities. When we put our numerical values in, we'll be putting in molarity values. And then number 3, we exclude pure solids and pure liquids from our expression. So here I just want us to write the expression. So we have square brackets again for concentrations, and we've got carbon dioxide as a product. Remember, it's products over reactants, and it's in the gaseous state. Okay. So we have that stoichiometry is just a 1, so it's just CO2. And then our second product is a solid, calcium oxide. We exclude solids, so we are not putting it into our expression. Then we check our reactants, which will be our denominator. And we notice that it's calcium carbonate, also a solid, so we exclude it from the reaction expression here, this equilibrium expression. So our Kc expression here is merely just the concentration of the carbon dioxide. And if it helps you to remember that it is the numerator, put a 1 on the bottom because it won't change the value at all. Okay? So when we write these expressions, let's remember we check 3 things. The balanced equation, ensure it's balanced. Second, we look only for concentrations. When we put in our numerical values, we're going to be putting in molarities. Third thing is we exclude pure solids and pure liquids because those do not have concentration changes over time. Okay? All right.